So I thank organizers for giving me chance to present some of my recent works in the one-dimensional quantum droplets in quasi-periodic optical lattice. So in today's talk, what I plan to discuss with you that regarding the quantum droplets, and then we will discuss about the idea of Anderson kind of localization in multicolor optical lattice. And then is it possible to measure the temperature in this particular droplet arrangement? And can we utilize it for generation of higher harmonics and different kinds of pattern in this system? And I try to put forward a case that there is a possibility to realize time crystalline kind of behavior in this quantum droplets and some connections with the temperature. So let's begin. So the system in which we study, I'm basically working in the Bose-Einstein condensate system, which has been long predicted by the Bose and Einstein in 1925, in which they predicted that for bosons, if we go below to the critical temperature, then one can observe Bose-Einstein condensate effect theoretically. And this idea was experimentally realized in 1995 by Catterley, Cornell, and Wyman using the laser cooling and evaporative cooling effects. So theoretically, we can study the dynamics of this Bose-Einstein condensate using the Pitaevskii equation. And in this particular system, this equation tackles the kinetic energy term, potential energy term, interaction term, and the gain and loss factor, which are present in this particular system. So we basically work in the one-dimensional system, and the idea to reduce to one dimension is that we apply cylindrical harmonic confinement along the transverse directions, so that we make the condensate in a quasi one-dimensional region. One can study in the both and weak and strong interaction systems. So I am studying the system in the weak measurement region. So in this system, from last 25 years, lots of experimental and theoretical developments has been reported. Experimentally, bright and dark solitons were observed in this particular system in vortices, and Faraday waves were also observed in these cases. Interesting results like superfluid and Mott insulator phase are also observed in this particular system. In this talk, I'm going to focus on three of the important results which has been realized in this particular system. One is the generation of ultra dilute quantum droplets, which are very dilute quantum droplets in comparison to the classical droplets. Their number of particles are very less. And then next, the quasi-periodic lattices in which the Anderson localizations were observed by the experimental groups. And Braun et al. Has observed negative temperature kind of scenario in the Bose-Einstein condensate. So uh, uh, Petrov has predicted around 2015 that if we take the Bose-Einstein condensate, two-component Bose-Einstein condensate, and in that particular system, if our interatomic interactions are modulated such that the attraction of the interatomic elements can be balanced by the intra-atom repulsion, then it could lead to the generation of droplet state in the Bose-Einstein condensate. And this theoretical proposal in 2015 was experimentally realized in the Bose-Einstein condensate for the dipolar mixture and for the Bose-Bose mixture in both scenarios. And droplet states were realized. So the basic idea is that one can balance mean field interaction with the beyond field mean field interaction, and one observes the quantum droplets states. So in recent times, many works were reported in this particular domains, and Torrell group has reported that one can switch from droplet to soliton region by tuning the number of particles. One can switch from soliton to the droplet phase, and the signature feature of this particular droplet idea was that one realized the flat top density profile for the droplet state, and this can be achieved either through the number of particles control, and this Petrov has again proposed that this can also be realized by tuning the nonlinearity factor in the system. In recent times, these droplet features are also explored in the Bose Fermi region and other systems. So we basically start from the two-component form of the Bose-Einstein condensate, and using the scaling factor, we reach to the one-dimensional region. And here, in this particular one-dimensional region, if I compare with the standard Gauss-Pitaevskii equation, then one find it up here one more quadratic term, which is basically giving us the contribution of the LHY interaction in the system. And both this LHY interaction and the mean field interaction, which are represented here as G1xt and G2xt, they can be controlled through interatomic interactions, basically through the Facebook resonance effect. So we are basically working in this particular one-dimensional extended Gauss-Pitaevskii equation, and we try to analyze the behavior of this particular droplet, because droplet was proposed by the Petrov in the free space scenario. And Malamet group has studied this droplet feature in the one-dimensional region. So we first proposed this particular study by trying to find it out the form of the wave function in the first harmonic confinement region. And we estimated the wave function for this particular one-dimensional droplet case for the harmonic confinement. And we proposed this result that one can study this droplet feature in the regular harmonic and the expulsive harmonic trap, and we showed the impact of this expulsive and regular harmonic trap on the droplets, which we are seeing it up here, that when we are applying a regular harmonic trap, so we are getting a compression, and in the expulsive region, in comparison to the free space, more expanded, but in comparison to the regular trap, it is more expanded kind of scenario. Similar to the previous result, we have also showed that tuning the nonlinearity parameter, we can control the realization of this particular droplet flat top profile also. In this particular work, we by tuning this particular nonlinearity factor, we have studied the droplet to soliton transition, and in the harmonic trap, we proposed that we can switch from droplet to soliton phase by tuning the trap oscillator frequency. So, and recently we have shown that in this particular droplet arrangement, using the harmonic trap, one can basically manage the speed of this droplet in one-dimensional scenario. We showed that one can control the reversing of its trajectory. We can either slow it up or stop it up, this particular droplet in this phase, and collapse and revival of droplet were also proposed in the utility of this external harmonic confinement. And we have proposed that in this particular region, even crystalline phases can be also observed. And for this particular region, we have obtained the block kind of solutions motivated from the work of Parit and Professor Panigrahi, in which they have obtained super solid kind of phases for the quantum droplets. So next, now I come to the point where I started that I'm interested to explore this multicolor optical confinements. Multicolor confinements, what I'm targeting here is that here my optical lattice is a combination of four different kind of color, moving 1 to 4, and like here exponential term is present. So with the Fourier expansion, we can have and different kind of lattices which we can generate for this particular kind of multicolor kind of scenario. The idea is that we are motivated with the thing that if we analyze this droplet in the multicolor confinement, then one can explore the realization of Anderson kind of localization in the droplet scenario, which has been reported in the Bose-Einstein condensate. And one can study various kind of phases which are usually studied in the optical lattices system. So we started with this particular kind of potential, and we took the one-dimensional extended Gauss-Pitaevskii equation and taken this particular time-independent multicolor optical lattice, and we calculated the exact wave function form of this particular system. So through this particular case, we are able to tackle various kinds of optical lattice. Like we can, by tuning this P1 and P2 parameter, one can switch from pure optical lattice to bichromatic, trichromatic, and four chromatic optical lattices. And we can choose the regions in which domain we want to analyze the behavior of the droplets. So first we try to study this particular droplet in the pure optical lattice kind of confinement. And if you observe here that as we are increasing the depth of the optical lattice by tuning this particular P1 parameter, the corresponding experimental curves are given below side this particular region. So the depth of this particular optical lattices are increasing it up. But interestingly, like in the free space droplet were present, this enhancement in the potential drift result in the imprint of this matter wave lattice on the droplet profile, but droplet structure is not disturbed, or it is not collapsing it up. Whereas if I go to the region, when we move from optical lattice to the quasi-periodic optical lattice, here if we observe the bichromaticity of this particular system. So like if I start moving from free space to the optical lattice, and then gradually the quasi-periodicity is introduced in this particular system, then the droplet profile from the like free space scenario here, gradually the lattice patterns are getting generated on this particular droplet profile, and this is showing gradually the signature of some kind of localization is also happening in this particular lattice structure. Like if I compare it up in the beginning, the number of lattices, matter wave lattices which were formed here, gradually with tuning the potential depth of this particular bichromatic optical lattice, we are observing a kind of a localization effect in this particular system. So we explored this particular factor, that why this behavior is happening it up. So we plotted it up in the both in the pure optical lattice region, and when we are increasing to the quasi-periodic region. So it is basically what is happening in the this particular negative region. The balance of mean field and beyond mean field is in the counterbalancing each other. So that's why the droplet profile is not lost here. But when we go to the quasi-periodic region, in this particular region, then gradually this mean field term is dominating over this particular term, and a localization effect is resulting in the solitonic behavior. So we get a hint from here that one can switch from droplet to the soliton behavior by tuning this particular interactions. And we also explored this particular full color optical lattice in this particular system. And now both kind of density profile is imprinted on the droplet. Like here, bichromatic droplet matter wave profile is imprinted over the matter waves, whereas a kind of localization in the four color optical lattice is observed in the system. So motivated with that particular thing, that we are switching from droplet to the soliton region, what we tried to do two things. Is it possible to measure first the temperature of this particular system? And second, can we observe the droplet to soliton kind of transition in this particular quasi-periodic optical lattice? The negative temperature idea was given by Brun et al. In 2013, in which they proposed that if you have a higher bound system, then in that particular system, with the combination of expulsive and optical lattices, one can observe a negative temperature state. Although lots of controversy on this particular point, but many of the works were reported using this particular method for the realization of the negative temperature. So we have shown in 2022 that the combination of this expulsive and optical lattice kind of behavior, even in the quasi-periodic optical lattice also, one can realize negative temperature kind of scenario. So we started with this particular multicolor optical lattice, and with the approximation, we reached to this particular bichromatic region, and we tried to find it out the wave function for this particular scenario to estimate the temperature of the system. So we begin with this particular one-dimensional EGP equation. And for this equation 2 kind of potential, we estimated the kind of the wave function for this region. Now, we observe that like in the free space, we are observing the complete droplet profile. But as we are increasing the quasi-periodicity, so localization kind of effect is observed, which I discussed earlier. So we tried to measure the associated temperature for this particular system. So we estimated the entropy and the energy for this particular system. So we plotted a curve in between the change of potential depth of this quasi-periodic optical lattice and the temperature. So we observed that as we increase the periodicity or disorder in this particular system, gradually the temperature is switching from positive to the negative temperature, and the increase in temperature is connected with the idea of the Anderson kind of localization, which is forcing the atoms to coalesce at the central optical lattice site of the system. We are trying to understand this kind of oscillation which is observed in the temperature. We are trying to figure it out that why this kind of behavior is observed in this particular kind of temperature domain. We have observed this kind of behavior in the further studies also. We are trying to understand that, yet we have to find it out, figure it out that why this kind of oscillation in temperature is observed when we are going to the quasi-periodic domains. We studied the energy and the size of this particular system with the tuning of this particular potential depth. And if you observe that for small magnitude of the potential depth, we are in the droplet region. And as we move towards the high potential depth, that means a large quasi-periodicity in the system, that disorderness in the system, then the energy of the system switches to the positive side, and a kind of mixed state of droplet and soliton was is observed. And we measured the size of this particular system. Gradually, the increase in the beta is resulting into the decrease of this particular droplet size, which is showing the impact of fragmentation of this particular droplets. So next, we try to analyze this particular system that till now we have studied this particular thing in the stationary domain. We try to now figure it out that if we take it up that this system is not stationary, but the chosen potential which we are taking it up, it is varying with respect to the time. So, and lots of kind of patterns were observed in this particular uh, driven optical lattice system. So we try to analyze the behavior of these droplets in the driven kind of optical lattices. So what we have done, we have chosen a combination of multicolor optical lattice and the this particular linear trap. And as you are observing that here, multicolor optical lattice can be generated from here. And in the approximated domain, we calculated the wave function for the bichromatic kind of scenario. So we have bichromatic optical lattice, and a linear potential term is present in this particular system. So here, this delta T will give a drive for this particular system, and we can choose that what kind of drive we are going to provide to this particular case. So with this particular generic model, we are able to tackle various kind of experimentally relevant scenario. Like if I choose this particular delta and beta t as equal to 0, we will be into completely a free space scenario, which has been studied by the Petrov. And if I just keep beta t as a constant, then we will be in the linearly DC-driven kind of bichromatic optical lattice. And we can tune this particular delta t as a periodic or biperiodic. Then we can be giving it a drive of periodic or a biperiodic drive. And one can observe that if I want to give a small temporal perturbation in the potential depth of this particular system, then we can give a temporal dependency of this particular potential depth. So basically, this model is rich. It can tackle various kinds of experimentally relevant scenario. So we started with a first very generic kind of thing, in which we have taken a periodic drive for this particular system. And for this particular periodic drive, we have taken different kinds of strength of this particular periodic drive. If you observe here that beta is very, very small. So if beta is very, very small, so we are in a kind of mono periodic kind of optical lattice, and quasi-periodicity is very, very less. So that's why this droplet feature is uh, shown in the ABC kind of scenario. But with the increase in the drive strength, small drives is observed on the droplet profile. But as we increase the potential depth from 0.01 to zero point 0.5 or 0.95, so like I discussed earlier, that with the increase in the quasi-periodicity of the system, the disorder of the system is increasing it up. So one can observe in figure A, D, and G, the droplet profile is compressing it up, showing a kind of localization kind of effect. And with the increase in the driving from 2 to 4, these periodic patterns are getting more and more predominant. So uh, with this, we try to measure that what kind of frequency which has been generated in this particular situation. So I have taken delta cos QT kind of drive, where Q is 10 here for this case. So we observe in the FFT pattern that the this droplet is driven with this two fundamental frequency for this particular system. Now, but we thought that if we put some kind of temporal modulation in this particular system, then temporal modulation in the potential depth results in the generation of higher harmonics in this particular droplet oscillation. And these higher harmonics are basically a combination of the perturbing frequency which we have given to this particular system and the fundamental frequency of this particular bichromatic optical lattice. So here this KQ and 2KQ by 2 pi, basically they are giving us the fundamental frequency, and all of these particular higher harmonics which are being generated are basically combination of this P and Q factors. So this give us a thought and motivated us to look a effect of generation of time crystalline behavior in this driven by periodic optical lattice. Actually, time crystals were proposed by Wilczek long back in the many body system, that if we give some kind of quench to a optical lattice kind of system, then in the that's case, the system shows a spontaneous breaking of from time translational symmetry. And this has been shown that this oscillation is basically becoming the generated time crystalline oscillation is basically a integer multiple of this drive periods. And this has been experimentally also observed in the Bose-Einstein condensate system. So we thought to explore this kind of behavior in the driven system. And for that particular purpose, we took a linear driving in the biperiodic optical lattice, and we tried to use our model to study that particular effect. So, I've showed you that we have estimated the wave function for this particular kind of potential. So we choose here a linear drive with a constant potential depth. That potential depth is not changing with respect to time. And we are giving a linear drive to this particular system. We verified it that if I choose beta equal to 0, then we will be in the free space kind of scenario, and we are obtaining a droplet profile which is visible in the purple plot. And as we increase the beta magnitude, then the disorder is start appearing it up. If you observe this blue curve, which is for beta equal to 0.95, then here biperiodicity is visible in this particular system. So like we studied earlier, that as we increase the biperiodicity of this particular system, then then the uh, uh, then the periodic structures are getting form on this particular droplet profile. So we analyzed the density profile of this particular system, and like previously we investigated that for the low potential depth domain in the pure optical lattice, we are remaining in the quantum droplet region, and for the high magnitude of the beta, this stripe-like kind of patterns are formed in over the quantum droplets. Now, this driving frequency, which is your, if we change the strength of this particular driving frequency, then the periodicity of this particular this terms are connected, and if you can observe it up this periodicity, if you increase the strength of this particular delta term, then this periodicity is also enhancing it up. So we try to analyze that with what frequency this droplet is oscillating under influence of this particular linear drive. So we took a particular point for this particular droplet, like x is equal to 2 position, and we analyzed its dynamics for different potential depth. We analyzed it for a small magnitude of the potential depth and for the bichromatic optical lattice also. Now, it is visible in the A that with the increase in the strength of the potential depth, the height of this particular term is increasing it up with the time. So we measured the frequency of oscillation of this particular system. So if I focus over this choose an external potential, so we observe that the fundamental driving frequency of this potential is basically F and 2F, where this F is nothing but kV by 2 pi kind of thing. And for here in this particular curve, we have chosen V equal to 2. And for this particular case, the fundamental driving is coming out to be 0.27, whereas a second fundamental frequency is coming out to be 0.54. But here we observe that a third frequency is also generated it up here, which is not the driving frequency associated with the external trap. And this frequency is coming it up when the magnitude of this beta is increasing it up. If beta magnitude is small, so it has a small magnitude, but as we gradually increase the strength of quasi-periodicity of this system, then this strength of this 3F frequency is becoming prominent. So, so in the pure, even if I present in the small beta magnitude regions, then the system will be driven with the fundamental frequency. But if I increase the disorder of this particular system, then this new frequency is coming to be visible in the FFT curve. So next we try to analyze the system that if I change the velocity of this particular system and we enhance the velocity in its magnitude, what is the impact which is observed on the oscillation of this particular droplet? So what we observe, like if you see the FFTA spectrum of this particular droplet oscillation for V1, 2, and 3. So for this V1, the fundamental frequency is present at 0.135 and 0.27, and a small kink is coming at 3F kind of frequency. And if you keep on increasing V, then for V equal to 3 factor, like at 1.215, this is becoming prominent. So we are observing in comparison to the this two frequencies of this particular system, we are observing a generation of new frequency in this particular driven system. And now to check that is this crystalline behavior, time crystalline behavior is present, remain stable. So we try to check the density correlation function for this particular system. And we observe it up here that as we increase the beta magnitude, so for high magnitude of the beta, that means high potential depth, this 3f frequency is remain present in the system in the density correlation function also. And for a small magnitude of beta, this will be very, very negligible. But if we increase the beta magnitude, then this third frequency term is coming out to be seen it up. So next we tried to analyze the system that is it some kind of some combinations which are happening it up due to the presence of quasi-periodicity. What is the impact? So to analyze that particular thing, so what we have done next, that we have chosen a perturbation in the potential depth of this particular system. And for this thing, we have added a periodic perturbation in the potential depth of the system. And we were expecting it up like in the periodic case, which we have studied earlier, that it will lead to generation of higher harmonics and a combination frequency additional to the fundamental frequencies which are present in the this particular external potential. So we are observing it up that here these two fundamental frequencies 0.27 and 0.54 are present, and all the higher combinational frequency, this higher combinational frequency, because here in this particular system we have three frequency terms were present. One is this particular omega, another is your kV by 2 pi, and another is 2 kV by 2 pi. So three frequencies are interacting here. So all of these higher modes which are coming it up, higher frequency modes, we have estimated it up that these higher frequencies are basically a combinations of this omega and this fundamental frequency of the external trap. But this 0.81, which is the 3f frequency, which has been observed without the time perturbation, it is still present in the time perturbed case. And here we have estimated this particular case for very high magnitude of the potential depth for 0.95. We have observed it for the small beta values like 0.01 or 0.5. In that particular thing, this magnitude is intensity is very, very small, and it is becoming significant as we are increasing the beta magnitudes. So we are observing that that even in the temporal perturbation, this 3f frequency term is not dying down. So next, we try to correlate this 3f frequency with the temperature observed in the system, and we utilize the method used by the pronatal to estimate the temperature of the system, and we have connected it up with the frequency observed in the case. And if you observe it up, this is A is for the time independent case, that as we increase the beta magnitude, because localization impact is increasing it up. So that's why we are observing an increase in the negative temperature of the system, which is consistent with the result which we have obtained earlier. And we are observing a kind of, again, oscillation in the temperature with the crystal frequency, which we are trying to find it out that why this kind of temperature oscillation is coming it up when we are changing the disorder in the quasi-periodic optical lattice. Similar kind of behavior is obtained in the time-perturbed scenario also. And so basically, through this particular study, we tried to study the quasi-periodic optical lattice for generating various kinds of patterns in the system. And uh, we showed that with different kinds of driving and with different potential depth, one can control the kind of patterns which can be generated on the quantum droplets. Even through the potential depth perturbations, one can obtain a higher order of harmonics on this particular system. And we are proposing that one can observe a time-crystalline kind of behavior on the quantum droplets under the quasi-periodic optical lattice instead of pure optical lattice. And through the disorder of this particular system, the generation of this time-crystalline behavior is connected it up, and the potential depth and the driving velocity of this system is controlling the behavior of this case. And we try to connect the generated frequency with the temperature observed in this particular system. And this uh, can be thought of using a method through which temperature estimation can be done for this particular quantum kind of scenario. So with this, thank you.
Thank you. And it's very interesting talk. And so the session now is open for questions. You can directly ask the question. You don't have to click on the raise the hand kind of thing. Okay, let me start with the questions since I don't see anyone volunteering. But yeah, so I find this your work very interesting from the very beginning. I mean, you took this potential, which is like a mod phi cube kind of interaction, and a mod phi, and of course a phi 4, essentially your cross Pitaevskii equation. Okay, and you said something is attractive, something is repulsive, kind of interaction. So yes. Which part of the interaction is attractive, which is repulsive? Is there? You had two couplings, G1 and G2 or something.
Yes. So basically, their mean field interaction term, the cubic interaction is basically attractive factor in this two-component BEC. And that when one consider this fluctuation term, which leads to generation of quadratic interaction, so that strength is repulsive.
I see.
And because usually this LHY strength is very small. So experimentally, people try to reach a region where when this mean field interaction is cancelling it out and becoming very small, so that this quadratic nonlinearity and mean field nonlinearity become comparable, and one can observe droplet state.
Yeah. Okay, that's it reminds me the many-body aspect in the nuclear physics, where we know that it's a nuclear matter, infinite nuclear matter is a liquid, in the sense that the energy per particle, if you plot, there is a minimum in the density, which is the saturation density. I see that kind of a plot also in your first slide, where there was a minimum at a given density, and probably that is why you call it a liquid droplet or something, right? Okay.
Yes.
Okay, that is one part. The other part, what I was very okay, I mean, here, do you see a kind of a liquid gas phase transition kind of
Uh,
thing?
uh,
Something like a droplet to soliton transition, where the energy was negative for droplet and positive for soliton. Solitons are like a localized extended offset. I mean, kind of, yeah, many particle.
yes, yes, interesting. So, yes, we have observed that one can switch to droplet to soliton kind of behavior by controlling the particle number or the nonlinearity of the system, and through like that has been experimentally shown. And we propose that even through the external trap tuning, one can reach to that particular region. Uh, that profile. But this kind of transition, that liquid to gas kind of transition, uh, I have not explored. Uh,
Yes.
I have not explored that particular thing.
Yeah, I mean, typically, I mean, in nuclear physics, the binding energy per nucleon kind of decreases. I mean, that minimum, as you say, with temperature, and finally it becomes zero, where you define the gaseous phase, essentially.
Yes.
So that's the way to do it. The other thing, very interesting thing you told about the time translation, um, or time crystal thing of Wilczek that you were doing. That's a very interesting subject. You showed something on the bimodal frequencies uh,
Yes.
for the, say, density correlation.
Yes.
Huh?
Yes. Yes.
Is that is related to a fast order phase transition? I mean, I have seen that in many of these QGP experiment to look at the critical point,
Mm-hmm.
and the idea is, if you increase the temperature, the
Mm-hmm.
nuclear matter to quark matter transition is a second order crossover, and if you increase the density, it becomes a fast order transition. Okay,
Mm-hmm.
so we look at the phase structure in the density and the temperature plane.
Mm-hmm.
Fast order line must end in a critical point. Okay, so
Okay.
to look for a critical point, they try to see uh, to look for a fast order transition.
Mm-hmm.
If there is a fast order transition, it automatically tells you the existence of a critical point. Okay,
Okay.
so to look at the fast order transition, they see this density correlation having a bimodal frequency distribution. So that's why my question was that. I mean, have you thought about it? I mean, just this cropped up when you are showing this.
No, very interesting. Very
I mean,
interesting perspective.
just
No, very interesting perspective, and I will definitely look into this particular point.
fast
Like,
kind of
yeah, I
thing.
will check that this. I will see that density variation with the temperature, because we are estimating in the system the temperature, and
Uh-huh.
we have also the idea of the density, but I will have to look that how this density is changing with the temperature, and I will have to find it out if this signature of this first order transition is present in this
Yeah,
system or not.
that's
I
right.
will have to check it out, but this is very nice perspective. I will have to look into this particular aspect.
Thank you. Yeah,
I have a question here, Mike.
Sure.
See, Ajay, you showed that in the presence of an optical lattice,
Yes, sir.
you have a imprint on the droplet, right?
Yes, sir.
This if you see this augmented NLSC, it has a super solid phase which amounts to a constant background with density modulation. If you see the pictures of super solid phase, the density distribution pretty much looks like a periodic lattice on a background. So what I thought that maybe optical lattice, if you put then induce this kind of density distribution, then remove the optical lattice, that may be a way to create a super solid. Have you thought about it, or has somebody?
Very interesting perspective, sir. And actually, we have not looked this thing in the optical lattice kind of case. But interesting, if yes, I will have to look into this particular facet. I will definitely look into this, but because if I show it up this thing, then this will be a way through which to create a super solidity in this optical lattice kind of scenario.
Yeah. Thanks.
Thanks.
Ajay, you told something about this multicolor systems.
Yes, sir.
What is that? What is color there? I mean, is it a frequency?
Yes. Actually, I am referring basically chosen frequency of the optical lattice. So, if I choose 4 different colors of optical lattice, so I'm calling it a multicolor optical lattice.
Okay.